All right, so in this lesson, we're going to start taking a look at our new unit dealing with fluid mechanics and basically how liquids, among other things, actually have physical principles applied to them. And one of the things that we'll build towards, whether or not it's the primary focus of the AP exam, is getting a better understanding of fluid flow through things like pipes. So for me, one of the things I'm excited about, believe it or not, is to actually get an understanding on how plumbing, modern plumbing, actually works, at least on the basics. And so there's a lot of other cool things that we get to find along the way. The first thing that we want to take a look at is going to be a core part of what we end up applying throughout this unit, and therefore, let's start with that. We are going to take a look at, let me make certain that this is set correctly, density. Now, my experience has usually been with many of my students that they have studied density in one form or another in a previous science class. The most common is, usually the year before they get to me, they come to me from the waking nightmare that is chemistry, and a lot of times they've learned a little bit about density. Now, that's great, especially if you are one of those students where you've got some background on it, because, hey, that saves some work that you'll need to do to adapt to it here. But sometimes it also works against you because you have some preconceived notions. So we're going to show how we need to adapt things not only for the AP Physics class and the AP Physics exam, but also many of the conventions that are used that are a bit different, at least from my experience, from what students encounter in chemistry, are also the things that set you up for a future career in engineering. Because the variables and the other applications that we use are something that are actually used more commonly in professional engineering than some of the things that you may have seen in chemistry. Now, that's also going to be a double-edged sword because it may also prove to be a little bit more challenging than what you had seen just in chemistry. And we're going to set the stage as part of this lesson for any of you who may be watching who are preparing for the calculus-based AP exam, where there are some broader applications for different types of density that you may not be aware of. We're going to talk very briefly about it to set up for when you would apply it in the future, and those would apply more broadly not for a mass density, as we're going to be focused on throughout this section, but instead for a charge density, which you may encounter in a later unit of study in AP Physics 2 or AP CE&M, or whatever the subsequent courses you may take in your progression in your career. Okay, now that we've got a brief idea of where we're going with this, let's jump into density itself. The notes that I have on this, density is in its most common form, and the primary way that we're going to apply it is mass per volume. Now, it's kind of the best way to describe the definition on this. I'm going to say more broadly, the term density is applied in many different ways. There are many densities, things like a population density, or a mass density, or a charge density, or a probability density, once you get to the highest levels of physics. There are a lot of different densities, and they're applied in different ways. So broadly, the word density itself actually applies to some sort of quality or value divided over a spatial application. And basically what that means is we're spreading one concept and seeing how it spreads over an actual physical space is usually what it is, though a probability density isn't necessarily that. So this isn't a perfect definition, but it's a functional definition for what you're going to take a look at. And I do say quality divided by a spatial application because most of the densities that we're going to look at are going to be something per volume or per area or per linear along a line. For AP Physics 1, at least as of the recording of this video, that's not something that you'll need to worry about that much, but some of you may be looking to take APC in the future, and it's nice to introduce some of these ideas while we can. I will follow it up by saying what we are going to define as density, what we'll talk about, and this should carry over to the AP1 exam and the APC Mechanics exam, and many of the introductory classes. It is technically called the Volumetric Mass Density. This is the last time I'm actually going to use the full technical term on that, but I do want to introduce it so that we know that we've got extensions that go off of this. I would hate for you to watch this video and say, okay, Sanchez showed me what density is, and then later you find out that these other things exist and you feel Sanchez lied to you. Well, I don't want to set it up where I'm blinding you to the things that will come, but for our purposes, this is the technical term, and we're going to focus on how we're going to apply it in this particular unit and most of our applications, at least for this level of introductory physics. All right, now that we've got that, the actual equation. And as of the filming of this video, I don't know why I grabbed that. This is the representation that is currently on the current draft of the AP equation sheet. I read it a little bit differently, but I read it like this. Oops. Yeah, I am slowly getting used to this board. It is relatively new. Now, there are a few things that I'm going to bring up on this. In fact, I'm going to switch the ink color to emphasize the difference on this. Many of you may have learned the following. D for density equals mass divided by volume, M divided by V. These are saying the exact same things. The first thing you need to be aware of is this. This is how I draw the Greek letter rho. It almost looks like a stylized, maybe backwards number 9 or like an upside down 6 or something like that. This is how I saw it with my professors in university when I studied physics. I think they kind of drew it this way. The main reason why is, and feel free to bring up the AP equation sheet. I thought about bringing it up, but I want to keep things moving. Right now on the AP equation sheet, and the best way to see rho is almost like this, where it looks a lot like a P, so much so that I don't like drawing it to look like how it represents in the Greek. I like this because it's noticeably different, and so therefore with my students it kind of shows up differently. That being said, it will look like kind of a stylized P when you look at it. A great way to actually check this is go over and Google density and actually look for the equation. You may find the D equals mv, but that's something that is usually used for the chemists, where D is the density. Now, a lot of students end up liking that because it's very simple and straightforward, but in physics, capital D usually means diameter or distance or something else. D is a letter that we use quite a bit in physics, and so we try and give things more unique letters so that we can kind of get a better idea of what they are in context. In fact, you're going to see D as part of the analysis that we do in this lesson multiple times. Another thing is, usually when we do a mass, we'll usually do it as a lowercase m. A capital M has the implication that it's a big value sometimes, or a couple of other implications. In this case, we usually do mass as a lowercase m. The other thing that I'll point out is this. V, this is how you would simply write a regular letter V. Is that capital or lowercase? It's really hard to tell, especially on my board where I don't have the lines. So both I and to some extent the AP exam, if you look, they have little lines at the top of the V. I will do that so that you know the difference between volume, which is something we're going to look at in this section, and also velocity or speed. In physics, speed and velocity are so important that we basically reserve a lowercase v for that, and we don't actually use it for anything else, at least usually, because we're constantly looking for speeds and velocities. We're going to take a look at that later when we get to Bernoulli's equation later in our study of this particular unit. So to help emphasize those differences, I want to emphasize the difference in variables that might be the first thing that you encounter that's a bit different. So this is the equation you may be familiar with. However, this is the equation that will show up in my notes and also is the same equation that is used on the AP exam. My rho looks a little bit different than theirs, but both of them kind of look like P, and we also have P for power and momentum. So again, here's why I do it a little bit differently. All of my materials, I always write rho this way. Okay, now that we've got the equation introduced, rho is the density. Now, technically, as we mentioned above, I should, if I'm being extra precise, say that it is the volumetric mass density, but for our purposes, it's the main density that we'll be working with, especially right now. So I'm just going to refer to it as density. If we use a different density, I'll specify that when we actually get to it. So in this case, we have density. We have our mass of the object, and then we have capital V, which is our volume. Okay, units. So on this, here's the other thing that starts to get a little bit strange for students who are used to studying this in a different class, in particular chemistry. Because in chemistry, the chemists have refused to commit to one unit system. They'll use metric, usually they use metric across the board, atmospheres notwithstanding, but neither here nor there. We'll talk about that in a later lesson in this unit. But they use sometimes the CGS system, which is centimeters, grams, and seconds. They like parts of that system, and so most of the measurements for mass are done in grams, most of the measurements for size are in centimeters, and then time is in seconds. However, that's actually an entirely robust unit system used by astronomers, among other things, and with that you actually have different units for force. I'm going to mention it here and hopefully not again, but we are used to using newtons. If you use centimeters, grams, and seconds, the CGS system, you would use dynes instead. Instead of a joule, you would use erg. I'm not making those up. You're welcome to Google them to learn more about them. But I've always been semi-critical of chemistry because they'll use centimeters, grams, and seconds, but then they'll switch over to the SI system whenever they want to use forces, which is infrequently, but energy in particular. So the important thing on this is for us to embrace the SI system, because that's an important part of what we do in physics and what will be shown on the AP exam, among other things. And it's just honestly an easier way to work with it when you start connecting these things with other values. If all you're doing is what's in this lesson, you could be forgiven if you think, we should just use grams and centimeters. But when you start connecting it beyond this lesson, as we will in the next couple of lessons, you'll see the SI system is going to save you a lot of time and effort. Okay, volume. As strange as it sounds, our SI unit for length is meter, so a volume, the SI unit would be meter cubed. Now, cubic meter, meter cubed, is 1 meter by 1 meter by 1 meter. That's actually pretty big. That's probably, I don't know, about the size of a bathtub off the top of my head, or at least fairly close to that. So that's a large volume. Mass, as we've seen before, is in kilograms, not in grams. Now, many of the experiments we do, we might measure things in grams and centimeters because that's the logical unit to measure them in. But as we're going to see in this lesson, do yourself a favor and get in the habit of converting them to SI, which will pay off later in this unit. Okay, therefore, our density is preferentially in kilogram per cubic meter. That's what all of the materials for the AP exam are most likely going to provide to you, at least the AP Physics exam. I don't know what they're doing on the AP Chem exam, but probably using grams and centimeters as most of the chem classes end up doing. If you are in just AP1, you will not need these particular equations, but I am going to introduce them real quick as a viewpoint of something that will show up later in APC Mechanics or APC E&M or your later studies, depending on what you go into. There is an area density. And that would be represented by a lowercase sigma, which looks like this, and that's where you would take the mass divided by an area. Or you might have a linear density. This is the one that is more likely to be used, at least in the introductory materials, and it is represented with the Greek letter lambda, which looks like a little coat hanger. I apologize, my board is slightly out of alignment, and that would be a mass divided by a length. I'm not going to talk more about that in this video, but I did want to draw connections to that because depending on what you go into, you will see those later. And this is related to our volumetric mass density, which is where we divide it by the volume. We also have the linear mass density, which is a common thing to take a look at. Okay, now that we've got that, let's finish up with the introductory materials for density. One of the reasons that it's useful, this is often called a bulk property or a bulk characteristic. I don't know if that terminology is specifically used on the AP exam. I think in their prep materials they called it a material property. There are a bunch of different ways that I've heard it referred to, but in my engineering programs, the ones that I went through, we usually refer to this as a bulk property. Basically what that means is it is a property, a number that is the same for a material. And what I mean by that is the number stays the same if you have a small amount or a large amount. So a good example on this is we're about to get into. In fact, hey, that's actually one of the next things for us to bring up. Water, the density of water. Now, technically that fluctuates some based on its temperature and its salinity and so forth, but the regular value that we usually end up seeing is this. So the density of water, you all may have learned before, is 1 gram per cubic centimeter. In fact, I had a problem years ago when we were teaching this, because most of the students, when I would ask what the density of water was, they would say 1, and I would say 1 what? And they would say, well, I don't know, it's just 1. It's only 1 if you're using grams per cubic centimeters or an equivalent unit to that. If you've learned that the density of water is 1, you haven't been lied to, but that's going to hurt you in what we need to do. For us, we don't use grams and cubic centimeters. When you do the conversion to SI, which is what we want to use, you will find that the density of water is 1,000 kilogram per cubic meter. You will be seeing that in my lessons as we go forward, and most likely on the AP exam. That is the standard value for it. Now, we'd have to do a lot of conversion on this. I'm not going to show you how to do that. You're welcome to do that on your own. But I do want to emphasize that if you are someone who's in the habit of saying the density of water is 1, start working on retraining yourself now. It is 1 gram per cubic centimeter, but it is 1,000 kilogram per cubic meter. Which, if you're wondering, well, that sounds weird. Why should I trust you? Remember how I said 1 cubic meter is about a bathtub worth of space? Well, if you fill an entire bathtub full of water, that's going to be super heavy. It's going to be a lot more than 1 kilogram per cubic meter. This is 1 kilogram. It's about 2 pounds or so. That being said, wait, 2 pounds? Yeah, about 2 pounds off the top of my head. And so a bathtub full of water doesn't weigh this little. I can't, toss it up into the air. It's going to be super heavy. So this is actually a much more realistic number and is actually the real number for that matter. So 1,000 kilogram per cubic meter is what we will want to be working with. Some other things that are useful about density. So 1, because it's a bulk property, can be used for. There are a couple things that I'll introduce that we can use density for. So why do we care about this number? What can it do for us? Well, some of the things that it can do, because it's a bulk property, it can be used to identify materials, ID materials. So for instance, off the top of my head, the density of aluminium, or aluminum, is about 2,700 kilogram per cubic meter. So if I had a thing of metal and I were to find its density, and its density came up to about 2,700 kilogram per cubic meter, then I would have a good bet that I'm actually dealing with aluminium, or something made predominantly out of aluminium. It might be slightly off if it's coated in something. I believe these are actually made out of steel, which has a density of just shy of, it's somewhere in the ballpark of 8,000 to 9,000 kilogram per cubic meter. I think it's about 8,000 for steel. Copper is usually a little bit more dense at about 9,000. Now, the other thing that I want to emphasize on this is the bulk property. When it comes down to water, the density of it is going to be 1 gram per cubic centimeter or 1,000 kilogram per cubic meter, whether you're dealing with a pitcher of the material or if you're dealing with an entire swimming pool, assuming that we don't have any compressibility issues and they're at about the same temperature. But that's one of the nice things about the bulk property. It doesn't matter if I have a small amount of steel or a large amount of steel, it should have about the same density no matter how much of it you have, which is why we call it a bulk property, or I believe the AP exam calls that a material property. So one of the first things that we can use density for is use it to identify different types of materials, which we hopefully will take a look at, possibly as part of this lesson, but we'll see. Another thing that we can do is we can determine if the object floats. And that's where we're going to go with one of the next steps in our lesson today. And then finally, expanding on that, we can actually predict how much is submerged. Now, submerged is the fancy term for how much of this ends up under the water line. That's also why I have a picture. Because what we're going to do is basically walk you through a few sample problems that we're actually going to solve to make some predictions. Okay, so here's the intro information for it. Let's take a look at some of our examples. So, example 1. I have a wooden sphere. In fact, this is one that I got a little while back for some labs. I've got actually more of them back in the storeroom of various sizes. This was part of a lab set of equipment where we were finding the density of these objects to actually make predictions on them. So let's go through and actually apply that. Now, one of the other things that I've experienced is most of the time when students before physics have gone through to find the density, they would find the mass of the object using a balance or scale, which we will do. And then they also find the volume using something called Archimedes' principle. Now, in short, what that means is we put some water in a container like a beaker. We push the object underwater and kind of hopefully hold it just underwater if it floats, and then see how much this actually increases and take a direct measurement of the volume. But here in physics, we want to be prepared for other things, and this may be material that we don't want to actually put down in water. Maybe it's something that reacts with water, like magnesium. Well, it would be hard to submerge it. Submerging it might actually, one, cause an explosion, and or it might also go through and damage the actual equipment. So I would like to make a prediction about this particular ball without actually submerging it. Which brings us to what you are probably going to be asked to do in physics and broadly engineering in general, and on the AP exam. In this case, I emphasize the shape we're working with. This is a wooden sphere. So here's what we want. I want the density of this wooden sphere, and that'll be equal to the mass divided by the volume of it. Well, the first thing I can do is I can take the mass. I turn on the balance. I actually set that up, and then I've actually written it down beforehand so that I've got it. It comes up to a mass of 28.4 grams. 28.4 grams. Now, both I and the AP exam might give you the value in grams. Why? Well, partly to make your life more complex, and partly because that's actually what our scale, our balance, would measure it in. So we're trying to replicate what you would get in real life. Now, this is grams, which would be great for a chemist, but for us, we want this to be converted over to kilograms. We would divide by 1,000, and that should give us 0.0284 kilograms. You do want to build this skill. Both I and the AP exam and your intro physics class most likely will ask you to be able to convert grams over to kilograms because that's a common thing for us to do. Now we have the mass. Now we want the volume, which brings us to one of the other things that I'm going to introduce. So what I want to do is I want to deal with the actual shape itself. And when you go further in physics, you'll actually do this very often. So from math, I've learned that the volume of a sphere, and also, as a quick side note, this equation is on the AP equation sheet on the front cover beneath some of the standard values that they give you. But it is 4/3 pi r cubed. That is the equation for the volume of a sphere. So the only thing I really need is the radius of the sphere. Here's the problem. I can't actually usually measure the radius, at least not directly. I can indirectly by finding the diameter. Oh, I'm already holding up the equipment I'm going to use, the calipers. So I might try and use a meter stick, but especially for something that is a ball, a sphere, it can be hard to get a good measurement of exactly how wide this thing is, its diameter. And that's why, for this, I'm going to introduce, these are a piece of equipment called calipers. And they actually slide, and they are really good for measuring round objects. So here's what I can do. I can actually have it kind of squeeze this, and to get the diameter, I can kind of swing it back and forth and make certain that this is good and tight. If I've got it at the wrong spot, then it won't slide in, but I can squeeze it and then slide it back and forth. I know that this is going across basically the widest point on it, and I get that the diameter of this thing, I'm going to use little d for diameter, which is not uncommon, is 4.4 centimeters. Now, as I said before, both I and the AP exam will probably give it to you like this. Why are we giving you the diameter and not the radius? Because we desperately want to know if you can divide by 2. The actual reason is this, because it's what you can actually measure in real life. We're starting to get you ready for real-world applications. And we're also double checking that you remember to divide by 2. In this case, I actually forgot to divide by 2 when I was solving some of my notes beforehand, so I even made the mistake as well. This is my diameter. It is therefore equal to 0.044 meters. In this case, centimeters to meters is dividing by 100. So make certain you are able to do that. These are all common things expected on the AP exam. Okay, that means that my radius is actually going to be 0.022 meters, dividing it by 2. And therefore, when I plug that into my equation, the volume that I get for this thing, I'm going to check my notes instead of grabbing my calculator and solve each of these. Feel free to pause the video and then go through and actually check this. I have been known to make mistakes, but it is 4.46 times 10 to the -5th meters cubed according to my notes. Okay, great. So now that I've got that, my density can be found by taking my mass, which we said was, let me check my notes again, it was 0.0284 kilograms, 284 kilograms, divided by the thing we found here, which is 4.46 times 10 to the -5 meters cubed. Now, if we were using grams and centimeters, then these would probably be much more approachable numbers. It'd be like 28.4 divided by whatever this is, like 400 or 44 or something like that. I don't want to try and solve it in my head, but the numbers would be nicer, but we wouldn't have this in SI. And again, later in our lessons, we're going to see why we want the values in SI to be able to work with them. Okay, so I can go through and I can analyze this, and we come up with a density, when I work all this out, of approximately 637 kilogram per cubic meter. Okay, with this, I didn't actually bring up the materials beforehand, but we could go online. My favorite place to check is engineeringtoolbox.com, and I'm looking for a density of 0.637 grams per cubic centimeter or 637 kilogram per cubic meter, and I might be able to identify what type of wood this is actually made out of. Because there are actually many different types of wood. There's balsa wood, which is super lightweight, not very dense. Or you have things like ebony on the far side, which is actually something, type of wood that is so dense, it actually is more dense than water, and it sinks. Which brings us to the next thing on this. We can actually answer the question, will it float? In this case, we're going to say, will it float in water? And what we need to do is compare the density of your object to the density of what you want to get it to float in. In this case, and in most of our cases, it's going to be water, but you could actually use the density of ethanol if you were so inclined to do that. Okay, so in this case, we have our density of our object, which was 637, I believe. Yeah, 637 kilogram per cubic meter. If it is less than the density of water, 1,000 kilogram per cubic meter, then it will float. So I predict this will float in water. But I can take it one step further. We can actually find the percentage submerged, how much is underwater by doing the following. The density of the object divided by the density of the fluid you're putting it in, which is water. So we could do the following. 637 kilogram per cubic meter divided by the density of water, which is 1,000 kilogram per cubic meter. And then we would end up with 0.637. Please note that the units cancel out, so this is dimensionless. This is just a dimensionless number. In fact, this ties into something, you're welcome to Google it. It's called specific gravity, which is actually a more common way to deal with densities in engineering applications. The nice thing about it is no matter what units you use, you end up with a dimensionless number, so everybody agrees on the same number. But in this case, 0.637 is the equivalent of about 63.7%. So I predict a little over half of this is going to end up underwater. And that can be difficult to gauge when you're dealing with a sphere, because the halfway point is clearly kind of in the middle of it, but the 3/4 might actually not be 3/4 of the height. That being said, we know we're expecting a little over half of it submerged. So I'm going to put it down in the water. And when I look at it, I can see, hopefully you can, I don't know for certain, but ignore the bobbing up and down. I've definitely got a little over half of it underwater. So our prediction does actually come to fruition. All right, we're going to take a look at a couple of other samples, but I'm going to double check my recording. We'll be back in just a moment. All right, and we're back. I'm going to try and keep us moving. Once again, if you want to stop and double check the numbers, which I would recommend on at least some of these examples, feel free to pause the video and actually run through them. But I do want to give us a couple of other examples of different densities and how we can work with them. So we just finished looking at the wooden ball here, and we could go in and try and identify what type of wood this is based on its density. That was the first thing that I said that we could do with density. That being said, I'd rather keep us on task and checking some of the other things that we would predict, which is will it float and how much will end up submerged. Now this has a lot of applications in things like designing boats and other materials or shipping to know how much you could load up, that sort of thing, maximum cargo capacity. But Let's go to our next example. Let's try a slightly different one. I've got a tennis ball. Now this one, this isn't made out of one set uniform material like the wooden ball, so I wouldn't be able to do the first thing that we identified, which is identify the material out of which it's made, because it's not made out of a consistent material. But with this, we could still predict if it will float, which I think it will, just from my experience with a tennis ball before, and how much of it will be submerged. So our next example is going to be example 2, tennis ball. Now this is going to be very similar to the last one that we did. We still have a sphere. I'm going to fill in the information, putting this on a balance, a scale. I could go through and I find that the mass of the tennis ball comes up to, I think it's about 57 grams. Yeah, 57 grams, which is equal to 0.057 kilograms. This is worth getting some extra practice so that you can comfortably and reliably convert from grams to kilograms, because you're probably going to need to do that on the AP exam, or my exam for that matter. And if you go into this sort of thing for a living, either in medicine or engineering or science, you may have to do this on a semi-regular basis. Okay, now that I've got that, the diameter of the tennis ball, I used the calipers on that, and it came up to about 6.5 centimeters. And that is equal to 0.065 meters. Once again, a factor of 100 for centa and 1,000 for kilo. I'm going to keep us moving. Once again, we are using the volume of a sphere. So we're doing the approximation based on this being a perfect sphere, although it's not a perfect sphere because it has little indentations, but it should be pretty close. We'll see how good that is. If I've done my conversions and my calculations correctly, I was getting 1.44, sorry about the writing there, 1.44 times 10 to the negative 4th meters cubed. Now, when I take these combined, I would find that my density is going to be equal to 396 kilograms per cubic meter. And therefore, I keep doing that. That's not how you do a percentage. There. Percentage submerged would therefore be 396 divided by 1,000, which is going to be 0.396, or this would be about 40%, about 39.6%. I'm not going to be able to measure it that well, but we saw the wooden sphere had a little over half of it submerged. Now we predict the tennis ball will be a little under half submerged. So when I put this down in the water, hopefully you're able to see that. It looks about half submerged, but when I look at it, it seems a little bit wider above the water line. So I'd say that it's a little below, a little below halfway. Now, one thing that's going to make this shift, you may have even noticed it in the video, as soon as I put the tennis ball down in the water, it's fuzzy. Some of that fuzziness absorbs some of the water, effectively making it a little bit heavier. So after I put this down in there, it'll actually sink a little bit more. We're not going to take the time to do an approximation on that, but there are ways that you could expand to do that as needed. I want to keep us moving on this, but here's an application and a prediction that we could then turn around and test. Next up, the next one we're going to take a look at. I have a different shape. This is a pack of note cards. They're still actually sealed for the most part, though they're a little wonky. I've used them for this demo quite a bit, so they're getting a little on in age. But I have an index card pack that's mostly sealed up. Okay, so here's what I've got. Note cards. Let's see, I've got this. Note cards. Oh, note cards. And this is example 3. So on this, the shape that we are dealing with is technically called a rectangular prism. Now that's the fancy talk. The regular talk is it's a box. It's a rectangle, basically, except in 3 dimensions. So we've got the following. This, back, like that. If you want the 3-dimensional drawing. We have, this might be called the length, L. This might be called the height, H, and this might be called the width, W. In this case, the volume of a rectangular prism is going to be length times height times width. We basically find each of those values and multiply them together. This is a nice straightforward shape, but it does require us to take a little bit more measurements. Now, once again, I could use a regular ruler, but to try and get extra precise, I did use the calipers. Let's see what we come up with. So on this, I've got, and I didn't write them necessarily in the order, but I did give the values. I've got one of them, I think this is the length, is going to be equal to 12.7 centimeters. I believe the width is 7.6 centimeters. 7.60, and then our height is 1.75 centimeters, at least the way that I was orienting the object. So we've got, here is our long ways, our length, our width, and our height. Okay, now that we've got that, this is equal to 0.127 meters, this one's equal to 0.076 meters, and this one is equal to 0.0175 meters. You could probably call that 0.018 if you're rounding it to two significant figures, which wouldn't be a bad thing to do, though I can get very high precision with those. That being said, we're going to run with these numbers. The mass that I found when I put this on the balance, the scale, was 145 grams, which is 0.145 kilograms. Okay, multiplying all these out, I'm going to save some time and not even write the volume on this. We do have the equation. Actually, let's go ahead and write the volume just to be safe so that you can double check your numbers, and hopefully I've calculated these correctly. Let's see. Oh, I may not have written that one down. So I am going to skip over the volume on this one, but multiply those numbers together and what falls out should be your volume. I forgot I made a mistake on there and then canceled some stuff out. But I got, so I'm going to put a question mark here. The density that I got was 858 kilogram per cubic meter. Okay, now with this we could predict that our percentage submerged would therefore be about 86%. So I'm going to skip ahead a little bit. Hopefully you're kind of following along. Feel free to pause and double check your results. But let's see what we find when I actually take this and put it down in the water. So we expect that the majority of it will actually end up underwater. And hard to see possibly in my video, I apologize, but we've got a little bit of it poking out the top. Is it 15%? I don't know, but it is just a little bit poking out of the top. And so hopefully if I set up a good experiment, I could try and find out for certain if it is 86% submerged, but it certainly looks to be close to that. I would say it's about 90% underwater off the top of my head, just based on my eyes. Okay. We've got a couple more that I want us to take a look at to round all of this out, but the next one is the last one that is absolutely key, but I've got a few more for us to take a look at that introduce some new ideas. The main reason that I say key is our first example, we saw using the density to not only predict if it would float and how much was submerged, but also set us up where we could try and identify the actual material. Our second one reinforced that by doing something different and showing that we get a different percentage, and that worked out. Both of those were using the equation for a sphere. Now in example 3, we did similar setup, and we used the equation for a rectangular prism. The last one that is very important for us to take a look at is going to be, let's see, for the note cards I did that, let's go with a different color, let's go with, I don't know, blue. Example 4. So in this case, the example 4, let's go with a battery. So I've got a dead battery, an old Sony brand one apparently, but hey, look at that, it's blue. Now it's a dead battery, so I just need to actually toss it out or recycle it or do the things with it, which I will, but I like having it for an example here for us to do a prediction. Well, first off, I don't know about you, but I don't actually dunk batteries that often. I don't know if it's going to float or not. But let's see, let's make a prediction and see what we can work with. And finally, we're going to approximate this as a cylinder, the last of the common geometries that we are likely going to ask you to work with. Now, it helps if you have some of these either memorized or you're comfortable working with them, but remember, these equations are on the AP equation sheet, and they have been asked for you all to use in this format before. So in this case, I've got my battery. Let me check my notes on this. I did take the measurements once again with calipers. We have that the height is equal to 4.85 centimeters, and our diameter, once again, is 1.40 centimeters. Now we're dealing with a cylinder that looks like this, where we would have our diameter, D, and our height, H. So we are dealing with a cylinder, is the shape. The volume of a cylinder is equal to pi r squared, where r is the radius here, half of the diameter, times h, the height of this thing. Okay, so when I move or put all of that in for my battery, I ended up with the following: 7.47 times 10 to the negative 6th cubic meters. When I measured the mass of this thing, it came up to right at about 23 grams, which is 0.023 kilograms. When I solve all of that, I find that the density of the battery is a whopping 3,080 kilogram per cubic meter. Okay, well, I can't even go on to see how much is submerged because this thing isn't going to float. It's going to sink, is what I predict. It's got 3,000 and the density of water is 1,000. So let's see. I predict that 100% of it is going to be submerged. So I'm going to put this down in the water, and we see that it sinks straight to the bottom. Okay, great. So now we can predict not only we can work with cylinder shape geometries, but we can also see that not everything is going to float. Now, one of the things that I like to ask, and might be asked on the AP exam, but this is based on the density of water. If you take something like mercury, which is also a liquid, you could actually get that this battery would readily float in mercury, which has a density of something like 13,600 kilogram per cubic meter off the top of my head. If you want, Google, there's actually a video of someone taking a small pool of mercury, super dangerous, don't try that at home, but they put like a giant metal anvil made out of steel in it, and you can watch the steel floating on that mercury because it is lower density. So while we're constantly seeing if things float in water, that's just because water is a convenient and common thing for us to float things in, but it's not the only thing that you can apply this to. Okay. One of the last two that I want to take a look at, and we're going to go through those pretty quickly, just as a little bit of experience with it. I have modified equipment like this for a lab, but I have a Play-Doh container, which is mostly a cylinder, and I've actually filled it with little metal screws, basically, to give it an adjustable weight. So I have something of a known volume that I could measure it and it stays the same, and we could actually open this up and add or remove weight to try and get an outcome. One of the things that we do is we actually challenge students, okay, we want you to get this as close as you can to sinking without it sinking, and that's actually the challenge for them, to use these equations except in reverse, to actually solve for the mass that we would need in order to do that. Now, I didn't set up everything to do all of that, and I want to keep this video from going too long, but I will show you the basics on how to work with it. So I've got my Play-Doh, and then let's see, Play-Doh. Now, one thing that I'm going to bring up is, we've got that this is mostly a cylinder, but it's kind of flared where it gets thinner at the bottom and a little bit wider at the top. And the lid is also something that's a little abnormal. So my numbers, my predictions won't be perfect. That being said, it is closest to a cylinder, and I think it's going to be pretty well approximated by a cylinder. So I'm going to use that. My height is 5.5 centimeters, and my diameter is 4.1 centimeters. When I multiply all of this out, I did not actually end up finish solving this, it seems like. Oh, because I got distracted with the ring. Okay, so the mass of this, at least with its current mass, is 40 grams. Okay, so on this, I'm going to leave this as a challenge for you all so that I don't have this video running forever and a day. I'm going to say pause it now, run through, find your volume, and predict how much would be submerged. And then we will unpause in just a moment, and I will submerge this, put it in the water, and we'll see how this carries out. Okay, pause, unpause. Okay, whether you've done that or not, it's good practice, and I apologize that I forgot that one when I was running through my notes, but hopefully this is something that we've gone through a bit that you could now solve this. So let's see, let's predict. I'm going to put this down in the water. Oh. I'm shaking this around to get it nice and balanced, so hopefully it doesn't try and lean too much to one side. Now, we're just above the logo on this. If I had to estimate, we're probably about 65%, maybe 65% submerged. Now, one of the things that I would say on this is, again, this is a challenge that we had. Open this up, and now try and add or remove more bolts to predict, not just try it experimentally and say, okay, I'm going to add some and get it super close, but try and predict by adding the appropriate mass and check it with a balance or a scale before you put it in the water and have that as a competition. So maybe you want to see it's 40 grams right now, solve for how much you would need to get its density to be very close as you can, to 1,000 kilograms per cubic meter. Okay, the last one that I want to take a look at, or at least put on your radar, is this. It's actually a ring. Example 5. Let's see, let's go blue. A ring. Now I'm going to show you how to work with this. It's basically a hollow cylinder. And so we've got the following. Now this will still be an approximation, but this could be the same sort of thing that you would have for a pipe or a tube if it were long enough, but usually when it's thin like this, most people don't necessarily call it that. It might be better described as a ring. The height of this thing, the height is 1.9 centimeters. Now, a common thing that you encounter in engineering, especially with pipes, is we have the outer diameter, which I measured with the calipers, and that comes up to 3.6 centimeters. And we have the inner diameter, D in, which is 2.6 centimeters. So the thing about it is we've got material here in the outside part of the ring, but not on the inside. So how can we get the volume, or at least mostly, of this particular object? Well, here's what you do. You take the entire thing based on the outer diameter, and you find your outer volume, V out, based on this, using a cylinder, and ignore that there's a hole in it. Now you take the inner diameter and you find the volume of it. We're basically finding the volume of the hole that we have removed. So this is D in, and I would mark this as the volume of the inside, V in. Once you have those two, you know that this is how much you've removed from this in order to get our ring. So your total volume, V total, will be equal to V outer minus V inner. So that's how we could get the volume of just that. I will also follow up by saying that our mass, in my hand, is 3.44 grams. This is super lightweight. Now, when I go through and actually work with this, I'll go ahead and give you the results on it so that you can double check, but this would be a very good one for you to actually double check that you can do. 1.93 times 10 to the negative fifth cubic meters is the outer diameter. And the inner diameter, I found, came up to 1.009, basically 1.0 to 3 significant figures, or 1.01, I guess, times 10 to the negative fifth meters cubed. This gives me my total volume of the actual material would come up to about 9.21 times 10 to the negative sixth cubic meters. When I take that with the mass, I find that the density of this tape roll comes up to 370 kilogram per cubic meter. In other words, I predict that we would end up with about maybe 40% of it submerged. I'm rounding up a little bit. Here's the other thing. I know that this is going to be slightly off because one thing that I ignored is we actually have, this isn't fully thick with the one that I've got. There's actually a groove in here. So I am overestimating the volume. I'm saying the volume is much bigger, and since it's in the denominator, it is inversely proportional. Big volume will result in a lower density. And so I know that this is slightly off. We should have a smaller volume, smaller denominator, so smaller inversely proportional, should give us a slightly greater density, which means this won't be only 1/3 submerged. I predict it's probably going to be closer to a half submerged, but I'd have to take a lot more measurements and do a lot more analysis to get more refined results. That being said, I'm going to put it down in the water, and we find that it is, in fact, about half submerged. So a little bit more than the 30 or 40%, but we were overestimating the volume. Okay, that's the last of the materials that we wanted to cover, at least for this introductory lesson on density. One of the things that we have not shown, and I leave for you all as a bit of a challenge, is we kept finding where you've got the density is what you're looking for, and we give you the mass and you work with numbers to get the volume. So want, have. Now, other sample problems that we would like to take a look at are, we give you the density of the material and say the volume, and you predict what the mass is, or we give you the density and the mass and you find the volume that it would have. So the challenge that I had for you here would be comparable to those. That being said, especially at this point in our progression of physics, hopefully that's not too much of a challenge for you, and you will get some practice solving that as we move forward. But these are the key ideas on density, or specifically volumetric mass density. Now, we're going to turn over to some labs and develop the next steps in what we're going to be using. But you're going to find that the density of a fluid is going to be a key thing for us to analyze how it functions, the mechanics of it, throughout this unit. So you're going to see almost all of our equations are going to include density. So we want to be able to find that if that's a thing that we need. All right, until next time.